Hello everyone, and this week we're going to be looking at rotational motion. Okay, rotational motion is when things, well, rotate. They turn around in circles over and over around a fixed point. So there are some things that we need to know about when we talk about rotational motion. First is the angle theta in radians is defined as L over R, L being the arc length and R being the radius. Now, if you know the angle and you know the radius, you can also find L because L is going to equal R theta. Just like L is going to be, or actually theta is going to be kind of like displacement, where you have X. Instead here we're going to have theta. We're going to have angular displacement instead of linear displacement. Now, angular displacement is your change in angular position. So you take your first, or your final minus your initial, and of course that will give you how far that you went. Now, usually you start on the positive x-axis, and you can measure the angle between from the positive x-axis and where you began. Now, the angular velocity is just like regular velocity. Except it's going to be delta theta over delta t. And it is, the instantaneous velocity is something that you guys don't need to worry about, but it's there just in case. It's mainly for the 215 guys. Now, angular acceleration is the rate at which angular velocity changes. So it's just like regular acceleration, which is the rate change of velocity. This is the rate change of angular velocity, so it'll be delta omega over delta t. Now here we have the instantaneous acceleration, which is the limit as t goes to 0 of delta omega over delta t. This is another thing that is for pretty much the 215 guys only. And here we have the relation between omega and velocity. Now, angular velocity tells you how fast you're spinning. Velocity tells you how fast a point is going tangential to that circle that it's going into. Every point on a rotating body has an angular velocity omega and a linear velocity v. Now, velocity is your delta L over t, which is also, using the equations we had before, be r delta theta over delta t. Or it's just easier to think of it as your velocity is going to be r omega. Now you notice that your arc length, which is kind of like your distance, was r theta, and your velocity is r omega. There are some analogs there. All right, since r omega is how fast you're going, it stands to reason that the bigger the r, the bigger the velocity is, which makes sense. If you have something turning on a circle here, and the ones closer to the center, or the origin, or the center of rotation, will be going slower because and per revolution, they only go just a small circumference of a small circle. The ones out at the edge go much further in the same amount of time, so of course they're going faster. When moving in circles, we deal with two types of acceleration, tangential and centripetal. Tangential acceleration is how fast are you accelerating going in the circle. If you're going at a constant speed going in a circle, then you have no tangential acceleration. If you're moving in a circle, however, you do always have centripetal acceleration, which is that force that's pulling you towards the center of rotation. Well, here we have that the tangential is r delta omega delta t, which is alpha r, alpha being your angular acceleration times r. And when you start looking at the centripetal, it's the acceleration in the radial direction is v squared over r, which is r omega squared over r, and then it can be omega squared r. I know that you guys learned in lecture about v squared over r, and that's how I usually look at it. As you start doing some more work in rotational motion, you'll start noticing that things are very similar. You've learned some of these equations before. They're similar. They're a little bit different, but they are almost the same. So here's some of the correspondences. You have linear, you have the displacement as x, where rotational you have theta. You have velocity, or you have angular velocity. You have tangential acceleration, and here you have acceleration, which is also a tangential acceleration. Oh, yes, the little note, you must use radians. All of the angles that we're talking about are in radians. And here towards the end, I'll go over how to convert degrees to radians. Now, I just wanted to touch on the equations of motion. You guys will not have to worry about this in the lab. However, I just wanted to let you guys see that there are analogs between angular and linear equations of motion. They are, just about the same. They just have different variables stuck in there. So yes, things are, you've already learned this stuff, so it wouldn't be that hard to do if we needed you to. Okay, angular momentum is something that we definitely will be covering in class. And you don't have to necessarily know exactly what angular momentum, like how to calculate it, but you do need to know its effects. So angular momentum is just like how we talked about momentum in an earlier lab. It's very much an analog, except rotationally. If you have, of course, your angular momentum, or your angular momentum L equals your moment of inertia I times your angular velocity. Now I here is an awful lot like mass, because remember it was your momentum equals mass times velocity. Here I is the rotational analog of mass. It's its resistance to change. So if you have a higher or a larger moments of inertia, you're going to want to, you're not going to want to go faster. It's going to take more work to get things to go faster. Just like if you had a much larger mass, it's going to take more work to change the velocity of that mass. And here, of course, we have two examples. One of the ice skater. When she puts her arms out, she will move slowly. And then when she wants to spin fast, she brings her arms in, and that lowers her, lowers the moments of inertia. So because the angular momentum must be conserved, she'll end up going faster. And same thing with the diver who tucks in and then dives into the water. Okay, to convert degrees to radians, which is something that you will be doing quite a bit in this upcoming lab, what you will need to do is just take the degrees that you record using a protractor, multiply by pi, and divide by 180, and that will give you your angle in radians. Now, if you want to convert back, if you have something in radians, you just multiply by 180 and divide by pi. So what we're doing is we're just canceling the units of the degrees, or we're canceling the units of the radians and leaving the degrees. Now this will be our last camera lab, so we will have some Blinkie photographs to deal with, and they will be of dashes going around in circles. And guess what? You're going to be measuring the angles between those dashes. So what we're going to have to do is, well, first, do not use the first or the last line. We don't know if the camera started in between blinks, so that may or may not be a whole blink. So whatever's first, whatever's last, discard them. Some of them, not all of them, we put an X there to remind you not to use. Now to measure the angle, you measure or draw a line from the center to the beginning or the end of the first blink. Then draw a line from the center to the same place, but on the second blink. So if you did it from the beginning, do it from the beginning of the second. If you did it at the end, do it from the end of the second. What you want to have is you want to have a full, you will need to have two full, or one or two full on-off cycles. So you have to have an even on-off cycle in order to measure the distance. And then, of course, you'll use a protractor to measure the angle. And you'll be doing it quite a bit, so you'll get used to it. Okay, a few things in summary. Angles are measured in radians, or measured in degrees and then converted to radians. A whole circle is 2 pi radians. Angular velocity is the rate change of angular position. Angular acceleration is the rate change of angular velocity. The angular velocity and acceleration can be related to linear velocity and acceleration. And if the net torque on an object is 0, then the total angular momentum is constant. All right, guys, that's all that I have for this, this little lecture. So good luck, and we'll see you in lab.